Okay, picking up on where we left off, doing this limit here. Again, it is not in the form, its limit as x goes to negative infinity. It's not in the form constant over negative infinity. We have to achieve, let's write it so everybody can read it. We need to achieve constant over infinity, or negative infinity, as the case may be, because that we know the answer to. That goes to 0. And so we are just going to simplify this dude. Now here is a little fact. As x goes to negative infinity, the plus 6 and plus 8 are irrelevant. Plus 8 are irrelevant. Meaning this, that the limit as x goes to negative infinity of x cubed plus 6 over the square root of x to the 6 plus 8 is the same as x goes to negative infinity over x cubed over the square root of x to the 6th. I don't need to think about the plus 6 and the 8 when x goes to infinity or negative infinity. Negative infinity plus 6 is still negative infinity. Negative infinity plus 8 is still infinity. They just don't make any difference, so I can drop them. Now that's only true when we're dealing with infinity and negative infinity. Now dealing with this. Very technically, the square root of x to the 6th is the absolute value of x cubed, using what we just had up there. The square root of x squared was the absolute value of x. Very similarly, the square root of x to the 6th is x cubed. Now I need to figure out what this absolute value of x cubed is. So using my definition, using that the absolute value of x is negative x if x is less than 0, positive x if x is greater than or equal to 0, the absolute value of x cubed would be negative x cubed if x cubed is less than 0, or x cubed if x cubed is greater than or equal to 0. I can just take my official definition for absolute value, and instead of writing an x, write x cubed. Now I have to pick which one I want to use. X approaches negative infinity in this problem. X is approaching negative infinity in the problem. So that means x cubed, and we're going to really abuse notation here, is negative infinity cubed. Well, when I cube any negative number, that's going to be negative infinity. It's negative. So x cubed will be less than 0. Which means this. X cubed is less than 0 tells me that the absolute value of x cubed is going to be negative x cubed. So putting this all together, we had this. The limit as x goes to negative infinity of x cubed plus 6 over x to the 6th plus 8. We decided that since we are dealing with negative infinity, the plus 8 and plus 6 were irrelevant. Then we decided that the square root of x to the 6th was the absolute value of x cubed. And then we applied our definition of absolute value and came up with that the absolute value of x cubed was negative x cubed. which gives me the limit as x goes to negative infinity of -1. And now this is just the limit of a constant, and the limit of a constant is 1. And you should be able to check that by looking at a picture or a chart. So I'm going to get my function in here and we'll look at it and we'll pray to God that I'm right. X cubed plus 6 divided by the square root of x to the 6th plus 8. So, can I see it there? Let's zoom in a little bit. Okay, so I've got my original function in there. I'm just going to hit zoom 6 and see what we get. Now, disclaimer here, zoom 6 hardly is going to show me negative infinity, infinity. Zoom 6 only goes to -10 and 10. But in our kind of nice textbook world where textbooks are written with nice values and stuff, zoom 6, the standard window from -10 to 10, is usually going to show you what you want to see. And indeed, remember we said x goes to negative infinity. So I look on the left side of the graph, and it does look like my y-coordinate is close to -1. And if I do a trace, where's the trace? And I start going to the left, and let's go to the left, 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 left. And you can see that my y-coordinates down there are getting closer and closer and closer to -1. That on the extreme right side of the graph, my y-coordinate is getting closer and closer to -1. So again, you can check a lot of these things by looking at graphs. And this one does check. Okay. Last 3 problems in this section. For a lot of problems, there's going to be a shortcut for limits at infinity. Now, disclaimer, this is a shortcut for only limits at infinity as x approaches infinity and negative infinity. The following shortcut will simplify many of the problems encountered in this class. It does not work for all of mathematics. This shortcut works only for limits at infinity of rational functions. Rational functions, like we see there, fraction, a polynomial with the, or not a polynomial, a fraction where the numerator and denominator are both polynomials. When you have a limit at infinity of a rational function, you've got these shortcuts, and you can use the shortcut. Now, when using the shortcut to receive credit, you must state the relationship between the degrees you're using. Recall, degree, the concept of degree means highest exponent. So when I look at this first problem here, the shortcut applies. I've got the limit as x goes to infinity of a rational function, so the shortcut applies. And so what I look here is the degree of the numerator, which happens to be 3, is equal to the degree of the denominator, which happens to be 3. Sufficient just to write n equals d, but you've got to let me know that you're thinking about those degrees. And so sufficient just to write n equals d, I will know what you mean. And then it says up there, if the degree of the numerator equals the degree of the denominator, then the limit equals the ratio of the lead coefficients. Ratio just means fraction. So the fraction formed by the lead coefficients, so 4 over 2 or 2. And what I would be looking for an answer here is you tell me the relationship, and then you pick off those coefficients and simplify if possible. That's all there is to that one. If the degree of the numerator is less than the degree of the denominator, the limit equals 0. So what I would be looking for here is the degree of the numerator, which happens to be 3, is less than the degree of the denominator. Which happens to be 6. Degree just means less than. Or excuse me, degree just means highest exponent. Sufficient to write n equals d. Once you note that, And the shortcut applies here. Limit as x goes to infinity of a rational function. That's the only time this shortcut applies. X going to infinity or negative infinity, rational function. But once you note that the shortcut applies, there's all you have to write. And then the third one, if the degree of the numerator is greater than the degree of the denominator, the limit doesn't exist and approaches either infinity or negative infinity. You may use a calculator-generated table to determine if the limit approaches infinity or negative infinity. This is the only time a table may be used to determine a limit value. You can use tables to verify your answers, but not to find them. Here's the only time you can use it to find an answer. So we've got the degree of the numerator equal to 3, which is greater than the degree of the denominator, which happens to be 1. So numerator is greater than denominator. And so that makes the answer either infinity or negative infinity. Now somehow you have to figure out which it is. You can make a table if you want and see what's happening as we go to negative infinity. Or you can just kind of you can try to reason it out that as we go to negative infinity, x cubed, when we go to negative infinity, that would still be negative, times negative 3 would be negative, or would be positive. The numerator would be negative. You can reason it out, or just to make a table. And I'm going to go ahead and make a table. So I'm going to put my function into the y equals. And so we've got negative 3x cubed minus 2x plus 1 divided by x plus 5. Okay, so I've put my function into the y equals, and now I'm going to do table set, second table. Now, infinity table set. Infinity is way up there, or negative infinity is way up there, but I don't think I need to go terribly far. So let's just start at maybe negative 20 and count by ones. Actually, let me see if it'll let me count by negative 1, so it's getting smaller. And second and table. And so then we can see what's going on. Let me zoom in a little bit. So there's negative 20. And notice as I keep going further and further to the left, and we'll go, there we go, that's far enough. Notice as I go further and further to the left, going closer, negative 36, negative 37, so on, those values keep getting negative, more negative, more negative, more negative. So then I am going to conclude, since I see all those negative values, you could also make a graph, but the graph is a little less reliable. And especially if I did a better job on my table set. Let's do table set, and let's start it at 1,000 and change it by negative 100 each time. And I'll show you what happens on that table there. So second table. It's gone into scientific notation. Notice that's what all those E's are. And it's giving me 1,000. I need to do table set again. Second table set, start at negative 1,000. So where do we go? And notice I got all those E's, but notice everything is negative. Negative 1,600 goes to negative 7.7e. It's gone into scientific notation, but all those answers are negative. I took that away list a little too fast. All those answers are negative. So I did second in table set. I started at negative 1,000 and had it count by negatives, which then showed me that all my y values were negatives. And so I get to conclude that this guy is negative infinity. And that will conclude this lecture.